Okay. So today's topic is vapor pressure. We completed Henry's law. Do you have any doubt in Henry's law? Austin? Okay. So we are going to start. Vapor pressure. Vapor pressure. What is vapor pressure? So basically pressure exerted by vapor. So I'm just going to define it. The pressure exerted by the water vapor or vapor is called vapor pressure. Is called vapor pressure. Now see, if we have a container, this is a container in which water or any volatile substance is present. Up to this, there are two types of molecules here. One is surface molecule and another, which is below the surface molecule, is called bulk molecules. Always remember that if there will be question, which molecule will be vaporizing or which molecule will be converting into vapor, whether bulk molecule or surface molecule. So basically, in experiment, we found that surface molecule evaporates. Surface molecule evaporates. So basically, initially surface molecule is also bulk molecules, but when they get energy from heating, heat energy, they will be going upward because they gain heat energy, which will be in the form of kinetic energy. So it will move upward, and there will be force of the force of attraction will be lesser, and it can be easily evaporated. So surface molecule evaporated because they have high kinetic energy. From where this kinetic energy comes? So basically, when you are giving heat, that energy is stored in these molecules in the form of kinetic energy. And since they have high kinetic energy, that means low force of attraction. That means low force of attraction. If container is closed, then vapor pressure will be something, that means it will create vapor pressure. And if it is open, then vapor pressure will be equal to 0. It will not create any vapor pressure. So please do write it and let me know. Everyone done with this? Both of you?
1 minute. Done.
Okay. Now see, on which factor this vapor pressure depends. So I'm going to write a topic, factors on which vapor pressure depends. Factors on which vapor pressure depends. First of all, it does not depend on shape or size of container. Basically, if water boils at 100 degrees centigrade, it will not depend upon the shape or size of container, whether it is conical, whether it is cylindrical or anything. It will not depend on that. But it depends upon nature of substance. It depends upon nature of substance. How it will depend upon nature of substance? I'm going to take an example and I'm going to show you. Basically, if you are going to talk about vapor pressure of C2H5OH, vapor pressure of C2H5OH and vapor pressure of H2O. Just wait a minute, right? So you will see that vapor pressure of alcohol will be greater than vapor pressure of H2O. Why it is so? Because of hydrogen bonding. Hydrogen bonding is in both of them, and hydrogen bonding is also present in water. But the hydrogen bonding present in water is higher than the hydrogen bonding in C2H5OH, ethanol. Since the hydrogen bonding here is strong or more, that's why to convert this in vapor will not be that much easy as compared to alcohol, not alcohol, ethanol. And hence the force of attraction or bonding will be weaker in ethanol as compared to water, and it will be easily vaporized. That's why the vapor pressure of ethanol will be greater than vapor pressure of water. Are you getting my point? So basically this vaporization or evaporation depends upon the molecules, nature of the molecules or the nature of substance. What is the bonding? What type of bond is there? Are you getting my point? Yes or no?
Yes.
So you can also write vapor pressure inversely proportional to force of attraction. If force of attraction is greater, it will not be easily vaporized. Okay. And you can also connect this vapor pressure with boiling point. Basically, water has boiling point almost 100 degrees centigrade, and ethanol has boiling point around 60 degrees centigrade. So force of attraction is directly proportional to boiling point, you can say. Please do write it and then.
Done, sir.
Very. Now I'm going to give you a very easy question, and that is, arranging increasing order of vapor pressure. The first one is your ethanol again, C2H5OH. This is your ethanol. The second one is glycol, or you can say the IUPAC name, ethane 1,2 diol. Its common name is glycol. And the third one is glycerol. So please arrange them. Any answer? Humam and Asti. See, I'm going to explain. There is one OH, there will be hydrogen bonding. There will be two OH, there will be more hydrogen bonding. There will be three OH, there will be more hydrogen bonding. And that's why, or you can go for, always remember that, force of attraction is directly proportional to molecular weight. So as you can see, the highest more, so vapor pressure will be lesser. So it will be like this. Is that clear?
Yes, sir.
Please do write it. And then we are going to the next. Can you change the slide?
Done, sir.
Are you done with this?
Yes, sir.
Okay. Now I'm going for substance. On the basis of volatility, we divide this substance into two parts: volatile substance and non-volatile substance. Volatile substance is the one which will create vapor pressure that will be converted into vapor pressure. That means vapor pressure is not equals to zero. It will have some vapor pressure. And non-volatile substance will be one which will not create any type of vapor, that which will not be creating any type of vapor pressure. That means vapor pressure of non-volatile solute will be zero. For example, volatile, we can go for water, we can go for ethanol, methanol, and all, etc. And for this, you can go for urea, glucose, sucrose. These are all non-volatile substance. If you are going to plot a graph between vapor pressure and temperature, the graph is in between vapor pressure and temperature. The graph will be like this. First, it increases with increase in temperature. Vapor pressure also increases. After some time, it will be constant because at a certain temperature, all the substances will be converted into vapor. That's why. Like if you are going to boil water, a temperature, if it will attain a temperature of 100 degrees centigrade, then all the water will be converted into water vapor. So please do that. Let me know when you are done with this.
Done, sir.
Very good. Next topic is vapor pressure of solution containing two volatile liquids. That means in a solution, you know that solute and solvent is there. So both are volatile. So I'm gonna take an example with the help of this. There is a container and there is another container. Two container is there. And both container contains volatile liquids. Let's say in container this, the left one, you have A particles or substance of A, and in the container B, right container, you have substance of particle B, substances of B. Both are volatile. That means both will be converted into vapor and both will vapor, apply or exert pressure. Always remember that when in a container, if only one type of substance is there, it will be represented as P naught A. This naught basically symbolize that it is pure. That means in container only this particle is present, and we say vapor pressure of pure liquid A or pure liquid E. So in the same way, we are going to represent it by P naught B, and it will be called as vapor pressure of pure liquid B. Pure liquid B. Actually, what happens, what I am trying to tell you is that if you have water, you are going to boil it. You will be boiling the water at 100 degrees centigrade. That means at temperature 100 degrees centigrade, the water will be in vapor form. Now, if you are going to mix some of milk in that, then the vapor pressure, just take another example, same example. There is a container in which, what I say, water is there. You are going to boil it alone. And there is a milk in which there is a container, another container in which you are going to boil it. There will be another boiling point. There will be other boiling point. Basically, both will have different boiling point. Now you are going to add them together, water plus milk. This solution will have different boiling point. So it is very important to differentiate between them, because when it will be pure, it will have different boiling point, and when they will be mixed to form a solution, it will have different boiling point. We will see how, or it may be same boiling point. That depends. Okay. Now see what will happen. If you are going to mix them together, AB molecule will be here. AB molecule will be here. Now, here we are going to talk about PA and PB. Whenever in a container more than one substance is present, we are going to represent it by PA and PB. And we said PA is basically we use partial pressure of A. Whenever more than one substance is there, and this will be partial pressure of B. Is that clear, everyone? Both of you?
Yes, sir.
Now see, if you are going to calculate mole fraction of A here, it will be equal to 1. Why it will be equal to 1? What is the formula of mole fraction? Mole fraction of A will be equal to number of moles of A upon total number of moles in the container. And you know, in container only A is present. So total number of moles will be Na, and it will be equal to A. Zeta A, that means mole fraction of A will be equal to 1, and mole fraction of B here will be equal to 0, because there is no number of moles, or there is no substance of B that is present in A left container. If you are going for this, mole fraction of B will be equal to 1, and mole fraction of A will be equal to 0. But in here, if you are going to see, mole fraction of A plus mole fraction of B will be equal to 1. As I told you that sum of all the individual mole fraction will be unity. So please do write up to this. Then I'm going to introduce Raoult's law. Let me know when you are done with this.
Done, sir.
Very good. Now see, I'm going to apply. I'm going to explain Raoult's law, and then we will apply this Raoult's law for this container. Okay, so write with me. According to this law, in a solution, partial vapor pressure in a solution, partial vapor pressure of each component is directly proportional to mole fraction of that component. So basically, first you are going to write it and then I'm explaining this. Just let me know when you are done with this.
Done, sir.
Very good. So what does this Rawls law say? There was container of a solution in which oh, wait a minute, in which A and B both are present. Now, according to this law, it says that partial pressure of A, whatever is the component that is present here, as I have taken A because A was in the container. So partial vapor pressure of A directly proportional to mole fraction of E. Is that clear? This is what Rawls law says. Partial vapor pressure of each component will be directly proportional to the mole fraction of that component. To remove this proportionality sign, I'm going to use K, and this is your proportionality constant. This is your proportionality constant. Proportionality constant. Now, what is this K? So to know about what is this K, I'm gonna explain this. Let's say let A is pure. Let A is pure. So you know that when A is pure, this partial pressure will be written as P naught A, right? Yes or no? When
Yes.
A is pure, it will be written as P naught A, and K will be as it is. And when A is pure, that means only A is present, then the mole fraction of A will be equal to 1. Yes or no? So I'm going to write it here. Let A is pure, then that means PA will be equal to P naught A, and mole fraction of A will be equal to 1. Yes or no? Both of you, Austin, why are you not responding?
Yes, sir.
Is your mic not working?
No, it works.
Okay. So are you getting it all? When A is pure, that means PA is equal to P naught A, and zeta A, that means mole fraction of A will be equal to 1. Now, P naught A, from here, from this equation, you can see the value of K is P naught A. So we can easily replace this K with P naught A, and we got a formula: partial pressure of A is equal to pure pressure of A into mole fraction of A. In the same way, you can go for PB. Partial pressure of B will be equal to pure pressure of B into mole fraction of B. Everyone getting my point?
Yes, sir. Yes.
Now, please do write it up to this. Everyone done with this?
Yes, sir.
Okay. Now see. As you know that there is a container, there was a container in which A and B is present. In which A and B is present. And as I derived a formula, PA is equal to P naught A, P naught A, and Zi and PB is equal to P naught B zeta. Now, according to Dalton's law of partial pressure, If you have heard about this, Dalton's law of partial pressure, total pressure will be equal to sum of all individual partial pressure. Individual partial pressure. That means if you want to calculate total pressure of the container, it will be equal to the sum of all individual partial pressure, and you have two individual partial pressure, that is your PA and PB. If you are going to add them, you will be getting the total pressure, and you can also write at the place of PA, you can write P naught A zeta A plus P naught B zeta B. This may look tough, the equation, but it's very, very easy if you will go step by step. PA is partial pressure. I'm going to write it here. Whatever is given, please do write with me. PA we already know. Partial pressure of A. PB is your partial pressure of B. Zeta A is equal to mole fraction of A, mole fraction of A. Zeta B is equal to mole fraction of B. And also PT is total pressure of the solution. Total pressure or pressure of the solution, you can write. Pressure of the solution. Please do write it. Then we are going to have a numerical on this, which is very easy. You know how to calculate mole fraction. Then you can easily do this. So just let me know when you are done with it. Are you done with this?
Yes, sir. Yes.
Mom? Okay. If 0.78 gram of benzene. Everyone knows the chemical formula of benzene, yes or no?
Yes, sir.
C6H6. And 0.92 gram of toluene. Toluene is basically C6H5, CH3. So basically C7H8 you can write or mix. Find partial pressure of benzene and toluene. And also total pressure, that means pressure of solution, and also total pressure if P not B, that means pure pressure of benzene is given as 400 mm Hg and P not E, sorry, T, small t, this is given as 200 mm Hg. So basically this is your pure pressure or vapor pressure of pure, vapor pressure of Vp, that means vapor pressure of pure benzene, and this is your vapor pressure of pure toluene. Please do that. Let me know if you have anything. If you don't understand the question, just let me know. Are you able to solve it?
Yes, sir. Yes, I can.
Okay, please give it a try. Any answer?
Oh, 1 minute, sir. Mole fraction.
Okay. Partial pressure of benzene. That's good, Austin. Very good. And also tell me about the total pressure. And Mohammadin, please do so. Very good. What will be the unit, Austin?
mmHg.
Okay, very good. Let me know. Mom, what is the mole fraction of benzene?
0.52.
0.52, not, it will be 1/2, 0.5. Okay, okay. Let me know number of moles that is given mass upon molar mass. What is the molar mass? 78, yes or no?
Yes, sir. 78.
So it will be cancelled and you will be getting 0.01, or you can write 1/100. Okay.
You asked moles of mole of benzene, right?
Yeah, mole of benzene it is.
Yeah, mole of benzene I got 0.1. Mole fraction I got 0.5.
No, no. Oh, wait a minute. What you have got number of moles number of moles of benzene will be here 0.01. Yes or no?
Yes, sir.
Just wait a minute. Now 0.01. If you are going to calculate the number of moles of toluene, it will also be 0.01, right?
Yes, sir.
Yes or no? What you have calculated?
0.52.
No, it's wrong. It will be 0. Let me show you. Let me just show you. First of all, if you need to calculate, you are going to write pure pressure of benzene into mole fraction of benzene. So pure pressure of benzene is given. Now what you need to do? Calculate mole fraction of benzene. So mole fraction of benzene will be equal to number of moles of benzene upon number of moles of benzene and another which is toluene. Number of moles of benzene has a formula, given mass 0.78 upon 78 upon molar mass 78. Again here you are going to put the value 0.78 upon 78 plus number of moles of toluene. It is 0.92 given mass upon 92 is the molar mass. What is the molar mass of the toluene that you have calculated? Humam?
92.
Okay. So if you are going to solve it in numerator, you will be getting 0.01. So here you will be also getting 0.01 and here you will be getting 0.01. So after solving it, you will be getting 0.01 upon 0.02 and decimal will be cancelled by decimal, and here you will get mole fraction of benzene as 1/2. So you are going to write it 1/2 and you will be getting 200 mmHg. What is this? This is partial pressure of benzene. Okay. Now, if you are going to calculate partial pressure of toluene, that will be equal to pure pressure of toluene into mole fraction of toluene. So what is the pure pressure? That is given as 200. And in order to calculate mole fraction of toluene, you can use this formula directly. If you know the mole fraction of another quantity, 1 minus mole fraction of benzene. So we already calculated mole fraction of benzene is 1 by 2. And if you are going to solve it, you will be again getting 1 by 2. 1 minus 1 by 2, 1 by 2. And the partial pressure of toluene will be 100 mm Hg. And then if you are going to calculate total pressure, that will be equal to sum of individual partial pressure, that is 200 plus 100, that will be equal to 300 mm Hg. Isn't it easy? Can I change the slide?
Yes,
Okay. Now we are going for a graph that is this. In NCERT, it has been also written like this. Now, the graph, if I'm gonna write, first of all, I'm gonna tell you what is what. So basically, this is y-axis, which represents mole fraction. This graph basically is for solute and solvent are separately, and then for solution. And this y-axis is for vapor pressure. Okay. Now see here, the mole fraction of one A is equal to 1, and mole fraction of B is 0. And if you are going to move from left to right, mole fraction of B increases slowly. And here, mole fraction of B becomes 1, and here mole fraction of A is 0. Now see, you know that these are directly proportional to each other. Partial pressure is directly proportional to mole fraction, and this is zeta B. That means P naught B is here. P naught B is here. And if you are going for this, I'm going to write it like this. I'll explain it. This is zeta A here, so this represents P naught A. Always remember this. Zeta B on the right hand side corner, you can see this is your pure pure B. So this is your pure vapor pressure. This Y represents vapor pressure. This is your pure A. So this represents pure vapor pressure of A. Now this black line represents PB, and PB is equal to basically P naught B zeta B. And this blue line represents PA, and PA is equal to, you know, that P naught A into zeta A into zeta. And if you are going to match this, if you are going to match this, you will be getting total pressure, P total, and this will be equal to PA plus P. This will be equal to PA plus P. So what you need to focus, you can see P naught B is slightly higher than P naught A. And this y-axis represents your vapor pressure. So according to this graph, this represents B is more volatile than A. This is what represents. I just take it anonymously. A has a lower vapor pressure in pure form than B. You can see B is higher vapor pressure, having higher vapor pressure. That means according to this graph, B is more volatile than A. So this is how we represent this Raoult's law on a single graph. Please do write. Let me know when you are done with this.
Yeah, done.
Okay. So basically, in the previous class, there were tests. How was it? Ashwin, did you submit the paper?
Sorry, sir.
Did you submit the paper?
Which one?
Previous, the solution.
Yes, sir.
Okay. Just wait a moment. Okay, so there will be again a test on Rod's law. Please